Before heading to the video, if you haven't subscribed the channel, do subscribe it and don't forget to click the bell icon for the latest update notification. If you like the video, do like, comment and share. Stay tuned with LearnBay.co. Happy learning!
So today I'm going to start with edge detection and hopefully this will be over soon. And then we will go back to filtering and finish filtering as well. Okay. All right. Now, for meantime, while we are going through edge detection, first we will have to define what is an edge. So what do you think an edge is? Come on, anyone?
That differentiates between the object and background.
Okay.
Shape and size of object.
Shape and size of object? Are you sure you will call that edge?
Like face, if you want to see the face. The face has a shape, right? And if eye and all this different parts has a different shapes.
Okay. Okay, no problem. We will see how to go ahead with it. Okay. Okay. Basically, edges are kind of sudden changes that happen in an image, okay? Certain discontinuities. Okay, so sudden discontinuities, let me explain what does it means. Okay, so basically origin of images, edges are caused by a variety of factors. So there could be normal discontinuity, there could be a depth discontinuity, there could be surface color discontinuity and illumination discontinuity, okay? So what it means is there is first like what is happening on the surface, then there could be edge based on the edge itself, depth. Once the picture is finishing or when their lines are closing, it will look like they are joining somewhere. Okay, and then you have surface color discontinuity and illumination discontinuity, okay? Okay, so if I were to characterize it really fast, and if I were to kind of explain this, edge is a piece of rapid change in the image intensity function. So what we want to say is, if there is a sudden drop in the color or in the code of the picture, that you can maybe characterize as edge. Okay, so how will it look like? Something like this. So you know what, let me draw this. It is better like this. So let's say you have an edge. So I will draw a very thick one. So let's say this is an edge, okay? And so nearby background is white, and let's say this is green. So the green will have some code of its own. Okay. So if I were to mark them, let's say there is an axis. Okay. So how will the color code look like if the white? Okay. So let's imagine if it is pure green, it is 0, and if it is pure white, it is 255. Let's imagine like that. Okay. Let's imagine there is only a green channel available to you. So if I were to draw a dotted line just to see the correspondence there. Okay. Now till it is 255, it is going to be up, but then there would be a sudden decrease and then a sudden increase once the line is over. See this? What happened? That sudden increase and decrease, can you see that?
Yeah.
Okay, good. This is what this picture is also representing, if you look very carefully. So let me go back. So this is the direct intensity, okay? So around the horizontal scan line, you can see when it is white, it is close to 255, but when it comes down, let's say it comes down very immediately fast. So let's say it is 255, and this is close to 0, okay? Okay, but if I wanted to ask you, by looking at this, if mathematically you have to make an assumption how to calculate or how to get an edge, how would you do it? If mathematically you have to get a handle on the edge, how would you do it?
We'll have to take some part of the image and then measure the change there.
But how do you measure the change? Like, it's a very simple idea. You want to measure the change of nearby pixels, but how would you do it?
Like wherever intensity is 0.
Sorry, again?
Yeah,
but
0.
But it might not be exactly 0. There could be some intermediate colors as well. Line doesn't have to be directly black to white, so you don't think as 255 to directly 0. It could also be some other color or some other shade, okay? But still, there is some commonality here. So can someone think how to measure a sudden change?
Huge difference.
Sorry, what?
Huge difference between 2 pixels.
Yeah, huge difference. But how do you mathematically measure that? Or what is the mathematical way to do this, Neha?
We can keep some value and based on that.
But remember, Neha, once you start thresholding, miss, if you want to manually do it, wouldn't you have to know everything in advance? Like I am talking about a general technique to solve the problem. Yes, you can come up with that, okay, whenever it shifts from black to white or black to white, it's okay, white to black or white or black to white, okay, that you already know. So you can hard code the numbers and you can live your life happily. But you do understand that's not how real world works, okay? A lot of these kind of lines would not be exactly like black or something. There might be some variation of gray. So how would you hard code that?
We can take a threshold, right? To this threshold.
But again, okay, so same problem, man. Picture to picture, it can vary, right? You're always thinking black to white. I'm saying don't think that. Think about different colors. Line could be of any color. So how would you differentiate the line? What would be a simple mathematical trick which should work in most of the cases anyways? Because thresholding, then you need to know which colors are you working with first of all.
We will not threshold previously, like we will go on a run. Like if suppose for this image difference can be 255 plus 0 by 2. So if greater than that, we can take maybe something like that.
Okay, but let's say, okay, the line is not white, it is actually gray then. So everyone is thinking in that direction only. So let's say if I take something like this, okay. Now it is not exactly too contrasting from the background anyways, but you can still see it as a line. So even if you try to do that, there's no guarantee with different colors it will work. Look, man, there is something very important written here, and I thought someone would pick it up by this time. How do you measure that rapid change?
Slope or?
Yes, finally some people got the answer. Yeah, The answer is slope, right? You can just take first derivative. What will happen? Okay, now imagine derivatives. How the derivatives work? Basically what they are, tan theta, right? So if you were to take slope here, it will come 0. Even if you take slope here, it is 0. So this is the line, this curve is the line. But what will happen when the line is first encountered? It will be tan some obtuse angle. That's why it will be, let's say, tan 135. So this will definitely be a negative value. And when will again it will try to go back, again you will get some tan theta value. Let's call it tan 45 or something. Okay, tan 45, which is going to be a positive value. See, normally it will remain 0. Look, colors are constant. It is not going to change. But once the color change is very sudden, there will be a peak, some kind of minima or maxima, whatever you want to think. And by doing the first derivative, you will come to know that is there a chance of a line being there or not. Get the idea what happened? What did we achieve through first derivative?
Yeah.
Okay. So basically edges correspond to extrema of the derivatives. It could be a minima, it could be a maxima as well. Okay, so I will explain you what does this partial derivative filter means. Okay, well, forget about that. Let's just see first. Okay. Now there are two dimensions, x and y. So the picture has an x dimension as well as y dimension. So let's call this x and let's call this y. Can you tell me if I were to kind of measure the change along x-axis, which of the two pictures, right or left, shows the change along x-axis? Anyone? So the picture grayscale. So you have to imagine now, and I will show you these things in OpenCV's demo as well. That once we run OpenCV demo, you can very easily see all this.
Left side.
You are saying that is the with respect to x, right?
Yes.
Okay, cool. Anyone else? Yeah, you are right. The left one is actually with respect to x, and the right one is actually with respect to y. How would you understand this intuitively? Okay, forget all the maths. We will show you the maths as well. But how intuitively you will understand? Like, is it respect to x or is it respect to y?
So on his face, you can see those vertical stripes, black stripes.
Yeah.
So based on that, I could figure it out.
Okay. Yeah. Look, man, that is what basically the previous equation was. Basically, they are talking about two functions, or you can take two functions at any point, and this is basically your. Then they are talking about discrete filter. So how do you know that if you want to take this derivative, how would it work? So basically what you will have to do is fx plus 1. So with respect to y, there is no change, okay? You only have to worry about fx plus 1, y will remain as it is, minus f normal x plus y. So if you are dealing with pixel 1, okay? Pixel 1. So now pixel 1 will have two coordinates. Let's just say two coordinates. So there would be x point and there would be a y point, okay? So there would be x1, y1, and pixel 2 is x2, comma y2. Okay. Now, while you are measuring the difference or while you are trying to get the change along x-axis, you only have to worry about whatever the function is on x level. the next one minus the previous one, but only on the level of x. Okay, it has nothing to do with the y. Y will remain as it is. So if I were to run a filter, what kind of filter you think I will be able to make it work? If I were to think about a normal filter, then how should I construct the filter for x derivatives and y derivatives? I just want to accentuate the changes bit on x-axis, and similarly I want to accentuate the changes on y-axis. So x-axis basically means what? That if you are going in x direction, there should be an immediate shift. So let's say to show immediate shift, I try something like this. It can come in both varieties. It doesn't have to be just one. So this kind of filter will show you changes or immediate changes in x-axis. And if you wanted to manage around y-axis, then you should come up with this kind of filter, or +1 first, then -1. Okay, so let's see how it exactly works. Okay, now basically there are multiple filters and different scientists have worked on these filters. Okay, so you will see there are two parts. One is x and one is y. Okay, fine. Because let's say your picture will have two dimensions, x and y. So you will have to kind of differentiate along x and y as well. Okay. Okay, so what is a pivot filter? And okay, so these things will look very similar once you look carefully. That they are doing nothing, they are just trying to accentuate. So Sobel is one of the best edge detector filters. Okay, even better than previous, because by this multiplication of 2, it is also trying to intensify the differences. So how does a pivot filter will work? So pivot has two parts, and I want you to note this down because this might be slightly useful while we will go forward. Although these all are just functions in OpenCV, so no one has to really remember the filters. But you should know how the pivot and Sobel filters are specially designed. Okay, so what do you see commonality between a pivot filter and a Sobel filter?
Vertical and horizontal orientation.
Yes, perfect. You can see the vertical and horizontal. So here you can see, now this is x. So on x, it has to go, let's say negative to positive or positive to negative, both will work, but pivot is negative to positive. And here on y, it is going, let's say positive then to negative. And similarly in Sobel, there is also intensification with this too. So it kind of intensifies the differences. And similarly here as well. And I will show you basically when we will run some OpenCV codes, I will show you how a pivot and Sobel filter looks different while you are trying to work with them. Okay. But they all do the same thing. You can apply with them with convolution, and they will accentuate the differences or the edges along x-axis and y-axis. And of course, you can combine them. You can apply both of them one after another. Okay. So basically, this is x gradient. So the color change in this x direction is this. Okay, this is the derivative of the function, and this is the derivative in y. So remember, see, when you are taking a derivative in x, then df or dou f by dou x is live. This is 0 because of course dou y it has no significance right now. Similarly, when you are taking the derivative along y-axis, the x part becomes 0, and only this is the part which is live. All right. And you can of course think as a combination that if you were to take both of the derivatives, there would be a kind of a vector if you wanted to calculate for both of them. And gradient point is in the direction of most rapid increase in intensity. So in whichever direction the intensity is increasing much rapidly, that is the gradient direction. And of course, you can get the angle if you want to. So it is very simple. Theta is tan inverse of dou f by dou by divided by dou f of dou x. Okay. Any problem in this slide? Because this is just basic maths, how basically you calculate the gradients. Okay, and of course you can get the overall strength as well. So you just have to take the square plus and kind of take a under root. So you get an edge strength of the direction of most change in the gradient, okay, or in the image itself. Okay. Now what will happen if I put some noise in the picture? Let's say there is an edge over there. So where do you think the edge is right now?
Near 1000.
Perfect, near 1000, there is a transition. But do you see the zigzag that is happening here? This is because of noise. So ideally you would have expected the picture to be something like this, okay? Smooth going and then around up and smooth going, right? Now problem with noise is when noise gets included, something like this starts to happen. It kind of throws around the values. Let's say, okay. Do you see any problem if, okay, the edge is there, let's say, we can see the edge very easily, let's say. But do you see any problem how the edge detection, what problems can edge detection face right now?
Sensitive to the change.
Sorry, can you say that again?
Sensitivity.
Sensitivity to change, very good. So what will happen to the derivative? Can anyone tell me?
Derivative also keeps changing in the when there is noise.
Sorry, I did not get the whole sentence. Can you repeat that?
The derivative also keeps shifting wherever there is noise also.
Perfect. Yes, that's the correct answer. The derivative basically will not be fixed. Okay, so what it means is something like this is going to happen. If you were to take the first derivative, now find the edge. Okay, now try to find an edge. Oh, sorry. Where is the edge now? If you were to apply the derivative, what happened here? Just now you see the problem, what noise does. Okay, it can create lot of filters and lot of even edge detectors immediately if there is noise, because edge detection is not easy then. You understand what is why the second image has been produced, or is there any problem?
So if we apply some kind of smoothing, then we can overcome here, right?
Yes, that's what we are gonna do. But you understand the second picture, how did we achieve that?
Yeah, because it's random, it's constantly changing, right? The direction.
Yeah. So because there is a sudden change all the time. So what I can do here is maybe not in this scope, maybe here, sorry. Maybe I can increase the overall, come on. Yeah, so see these sudden jumps here, maybe even let's go slightly bit closer here. Okay, see these sudden jumps here. So when you try to take derivatives here, that derivative or that jump is captured here. And there are so many jumps that now there is no way to know where the actual line or where the actual edge is. Okay, so that is the problem we are facing. Okay, so as you rightly said, you have to smooth it out first, right? So how do you smooth out?
Averaging it.
Sorry, what did you average it? Okay.
Average.
Okay, so idea is like say we can use a Gaussian filter, and this is where I will connect the Gaussian filtering. What you have already, it's not already, but this is I think where we stopped last time. Okay, so I told you like we will cover Gaussian filter as well. Okay, so now basically we can touch both of them, and now you will understand it much easily what a Gaussian filter is and how it is good or why it works. Okay, so what is a Gaussian filter exactly? First, what is a Gaussian? Okay, let's talk about a Gaussian just to make sure everyone is on the same page. So what is a Gaussian filter or what is a Gaussian function? That's all I want to know. Come on, anyone? Okay. So first, let's try to understand what is a Gaussian filter, because this is where both of the things really connect. Basically, Gaussian filter removes high frequency component from the image. Basically, it behaves like a low pass filter. Anyone knows what is a low pass filter?
Yeah, I mean, it will not allow the high frequencies, right?
Yeah, it will not allow any high frequency to go forward. Cool, very good. Okay. Okay, so what is a Gaussian equation? Can anyone remind me? So what is the Gaussian equation? Come on, you know this. Gaussian is
1 by 2 pi e to the power minus x minus mean by standard deviation.
2 pi
e to the power
e to the power minus
x minus mean by standard deviation.
2 sigma, I guess. Is this correct equation or not?
X minus mu by sigma square and 1 by 2 is, I mean,
No, it's okay. Basically, you can think like this. The whole thing has to be the squared. That's it. Okay. Cool. That is, if you remember this, that's a very good sign. Okay. So what are the properties of Gaussian? Some basic properties. Let's just talk about a few basic properties of Gaussian. Of course, you can define them in X and Y, and this is what the separability is. Basically, X and Y, both parts can be just separated out, okay, altogether. So you could have so if you are trying to express this in X and Y, so basically this is how the equation will look like, which you can immediately separate out in two different equations, okay. Okay, sorry. So how does Gaussian works? Okay, so let's draw a normal curve. Sigma, okay, and of course in this direction as well. So what is the property of Gaussian? Can anyone explain me?
95% data will falls under minus 3 sigma to plus 3 sigma.
Okay, and what? Okay, so what is the interpretation here? That is right. That is a good mathematical observation value. We understand, but what does Gaussian achieves? Or okay, let's say if I apply a Gaussian filter. So what should I be able to achieve? Okay, let me explain this in a slightly different way. Okay, so one of the purpose of Gaussian is basically, let's say if you have very high frequency values, or if the values are changing a lot, but let's say there is a mean, so this value is mean. Okay, now so what Gaussian is gonna do is, if you were to apply a Gaussian convolution, okay, if you were to apply a Gaussian convolution with this function, or this, yeah, let's call it a function, what's the problem anyways, and this is a Gaussian. Okay, if you apply Gaussian, what will happen? It will perform a smoothing effect. What it means is, let's say only values around mu, most of the values around mu will be retained. So what it means is, it will almost flatten the curve, or the extreme points that you are looking are almost gone, because in Gaussian most points are near
Mean.
the mean itself. So any kind of extreme points are gone if you smoothen it with the Gaussian. Okay, and it doesn't creates a box effect. So I will show you in OpenCV that if I were to just use normal box filter, let's say 1/9, so there is some patchiness. Okay, so what I mean by patchiness is, there would appear like there were different windows which kind of have averaged out the picture. So there is some patchiness that you can see in the picture actually when you apply the normal averaging or box filtering. But once you apply the Gaussian filter, the patchiness is very less. It is like a very well kind of stubbed, or it is very well smudged. So how Gaussian works is, the near the mean it is highest, and as it goes beyond, it kind of starts to decrease. Okay, so that is the effect of Gaussian. So the point is to use Gaussian in our favor. So first, let's say smoothen it out. Let's say we choose a Gaussian kernel and we will convolute it. So what would be my output? It would be, no, it would not be this smooth. Okay, it is just a representation. Of course, there still are gonna be problems, but it will be smoothing it out very well. And around the edges, now there would not be a sharp turn. That's the only thing, but still it is good enough turn to kind of get a handle on the edge. So still I can take a derivative and I will be able to get an edge, maybe not that fine an edge. Okay, and then what should I do? Then how to detect an edge?
First derivative.
Perfect. You can just take a first derivative and it will give you the edge. So it's a very simple idea. You take the signal, you smoothen it out. Here in this case, we are using Gaussian kernel. So you apply the convolution, it almost flattens out the noise, and then you take a differentiation. What if I were to multiply it with, or what if I were to convolute directly? Now commutative property is totally valid here. What is the output of this? G dash means first derivative. And if I were to convolute it, then what would happen? Anyone like this basic maths? It's nothing new that we're doing here. You can do the same thing. Again, the same edges will be there, right? Rather than doing it one step at a time, you can take derivative of your function and do a convolution, and that will give you an edge. So this is the derivative of a Gaussian. Okay. So, what is the first order derivative of a Gaussian? Anyone?
I mean, like I googled it, so should I tell?
Okay, fine. No problem then.
Uh,
Okay.
X
Okay.
by sigma
X,
cube
X by
under root 2 by 2 pi.
here itself.
Yeah, in the denominator. Yeah, under root 2 pi.
Yeah, that is constant, so that will be there itself. Okay.
E power minus x square by 2 sigma square. And overall, there's a minus in
There's a
the,
minus.
yeah,
Yeah,
overall
yeah.
also, yeah.
Yeah, because of this basically, because X is there, so that will come out here. Okay. So what does this denotes? Okay, for people who do not know, basically it will produce a function like this. Okay. Okay, this is the kind of this is like the first derivative of Gaussian. So if you were to convolute with the first derivative of Gaussian, what you will get?
We are getting one maxima and one minima, like, I mean, that kind of curve.
This is one maximum, one minimum. But again, now you have to understand. Now, if you take a derivative of Gaussian and convolute it with the noisy signal, it performs both, you know. It will smoothen the picture out and it will also get you the edge. Okay, so rather doing step by step, like first convolute it with normal Gaussian and then take the derivative, you can do it in a better way as well. You can take the derivative of Gaussian and convolute it. That will give you the same result. Okay, so it is associative property, of course, so you can apply this as well. So you can directly take a convolution and you can take the derivative of the Gaussian and directly convolute it. That will also give you the edge. Okay, so this is how it will look like, the derivative of Gaussian in x and y direction. You can see, as you have already stated, there would be one minima, one maxima in either both directions, x and y as well. Okay, because we are talking about pictures which happens to have two dimensions, x and y. So that's how we will have to apply our filters as well. So we will have to apply two filters. One is in x direction, one is in y direction. So these are two separate filters. How do these two things look like? How do these two filters look like? Can anyone tell me?
Yin yang.
Yin yang, or in most blunt way, if I had to say this, although this is not correct, okay, I'm already saying this, so please do not directly copy paste this idea. Now Gaussian, of course, is not directly discrete or something, or it doesn't go +1 to -1. If a Gaussian filter is going to work, so it will kind of dissipate from the middle one. So what will happen is, let's say there is a highest value of 5 and then it starts to dissipate. So 4 in this direction, 3.4, maybe 4.1, maybe this is 3.8, and as you go farther along, the values start to decrease even a bit. So that is what Gaussian are, or this is all the first derivative of Gaussian. This is not Gaussian. Okay, so this is how the Gaussian filter should look like, and the values will keep getting smaller as we go farther away. Okay, 2.9, let's say, based on the standard deviation, Gaussian will start to decrease. Okay, and this happens to be the x and y, and this is what can also give you some basis for what Sobel filters or Privet filters are trying to do. They are trying to create a differentiation in that left and right part, or upper and the top part, for y, x and y respectively, and that will give you the edge. Okay, and the best part is Gaussian is it can also smoothen out the noisy points, and I guess you can already know which one finds the horizontal edge and which one finds the vertical edge.
X direction will give us the vertical edge.
Yes, very good. That is the one point like most people make a mistake. So this will actually give you the vertical edges. And this will give you horizontal edges. Okay. Now remember, if you apply a much bigger scale or if you apply a much bigger filter, it will take average of much more points. Then it can like make up too much of averaging. That is also something you don't want. And this is what the filter idea was. Okay, if you remember this, and even in convolution, I used to tell you should not also go very too small. Let's say 1 by 1 pixel or 3 by 3 pixel all the time. But you should not also go 11 by 11 or like 15 by 15. Okay, like 5 by 5, 7 by 7 are good options. Same, remember this, when you apply Gaussian derivative filters, try not to apply in too many pixels at one time. So try not to create massive window or something. It will blur out way too much. Okay, but if you go 1 pixel at a time, then the noise is as it is. There is no change. Okay, there is no smoothing. So you have to be careful how to apply. Remember, smoother derivative removes noise but also blurs edges. Okay, so be careful. It doesn't mean like you can apply at any scale. If you apply at large scale or if you try to average out a lot of pixels at one point, everything will basically get too blurred and then edge detection will fail again. So you have to be very careful with this part. Okay. So Gaussian filter looks like there is a peak in the middle and then it dissipates and it becomes zero or around it, or it becomes very close to zero. And derivative filters are, they have like a positive and a negative area. Okay. So if you directly apply derivative filters, of course, they will smooth out the noise and they will directly get you an edge. Gaussian filter is just a smoothing filter that directly doesn't give you any kind of edge. Okay. But if you were to take a derivative of after applying that convolution, you can again achieve the edges. Okay, so it's equivalent, and it is most people prefer to directly apply derivative filter when they are trying to find out an edge. Okay.
There's one question here.
Sure.
Suppose I want to, like you said, like vertical filters are find the horizontal edges and vice versa. So suppose I want to do two things, like horizontal as well as vertical edges.
So apply both. It's not like one has to apply one. Of course, we apply X and Y always. So it does find if you're thinking like, what about these kind of edges? One second. So it's literally vector mathematics, guys. There is nothing special happening here. If someone is worried like, what about this edge? So what you will do here? Come on, if you want to detect this edge, then it has both components, right? You understand this. You can get this edge in both components. So let's say if there is fx, x and y, sorry. So you will basically get both of the components and that will give you this edge. So we just apply both of the components and we get any kind of edge that is possible.
My question was like you will apply when you apply filter, you will apply both horizontal then vertical, or it's like in that filter only you will apply both things.
Okay, so mostly in OpenCV I will show you, we do a call. Okay, so we basically, it depends like what you want to represent, but if we want to do it, we can do sequentially. Okay, so first we can apply dx dou x. Once the output is given, then we again apply dou y on that. Okay, so it basically achieves both of these, and again it doesn't matter, both of them are independent of each other. So you can apply dou y first and then dou x, and or dou x first and then dou y, doesn't affect anything. Okay, so in OpenCV, I will show you how to connect these things and how to kind of generate that filter. All right.
Yeah, sure.
Okay. Okay, guys, let's give me 1 minute. Okay. Okay, before we move any forward, any questions so far?
One question.
Sure.
So till now we saw filters with values like 1, -1, 0. This Gaussian filter may look like have some decimal values, right? How we
Yeah,
ran
yeah,
them.
it will have decimal values. You can, okay, so if anyone is not clear, you can use decimal values, okay, as well, if you wanted to. But you can kind of visualize this. So let me tell you how to do it, okay? So this is why we are switching back and forth, because unfortunately these two things are very connected to each other. So I cannot really separate these two things out properly. So this is why I'm switching on one slide to another. So that you understand how this will work. Okay, no problem. No, sorry. Okay, so this is, I think, what was your question, right?
Yeah, yeah.
Yeah, so this is what Gaussians are. In most simplest term, this would be a Gaussian filter in terms of X and Y. And if you want to note it down, please make a note of it, okay? It will be useful for you guys. So in terms of X and Y, this is what Gaussian filter looks like. Sorry, there is an under root, my bad, sorry. There's an under root here that is missing. Okay, this is how the Gaussian looks like. And this is how, if you want to understand, this is like one representation of 5 cross 5 where sigma is 1. Okay, so you can see the highest value in the middle, and you can maybe make a circle around it, and you can see that based on the circle and based on their application, it is slightly hard to make these circles here, but you will get a hang of it. Okay, and 0.22 actually is a closer circle, to be very honest. So you can see this I have just tried to create some kind of a Gaussian effect here, means you can maybe see the contours and try to understand. Okay, so overall, when you will sum all of them, you should get 1, okay? When you will sum all of these numbers, because it is discrete, so you cannot really go till infinity. All of them will sum to 1 exactly. But this is how a Gaussian filter looks like. Now problem is the multiplication will become very hard for you to do manually. It is not really integers that you can do very fast, but maybe you can write a numpy function and try to do this operation on a kind of a noisy points or a filter which has noisy points, and you can see the difference what it brings. Okay. And once we go into OpenCV, I will show you with the pictures, and this is how it looks like. Okay, it's a simple idea. I think you understand the effect of sigma, right? Okay, so standard deviation sigma determines the extent of smoothing. Okay, guys, remember, if sigma is very small, then what will happen? Come on, it's easy to visualize. When sigma is very small, this kind of surface will be created. Okay, so how what will be the impact on the smoothing? Basically, it will only consider very few points to average out, or very nearby points to average out. Maybe let's say 4 by 4 or 3 by 3, let's say, to smoothen out, because its impact will be felt very less. So on very few pixels, the impact will be felt. But once I increase the sigma, then what happens? The smoothing is across much broader number of points, okay? Because you can see it doesn't dissipate immediately. So see the color changes in this sigma, no, sorry, in this graph here, the color change that is happening. Imagine the red is the middle one. So this is like mu plus minus sigma. The yellow one is mu plus minus 2 sigma. And this light blue is mu plus minus 3 sigma, okay? And the blue one is everything apart. So imagine most of the points which are in red or green or red or yellow or some in light blue are basically gonna get averaged, but it is still a much bigger area compared to this one. So it will average out more points and it will create a much blurry effect. Okay, now Gaussian functions have infinite support. What it means is they can go in any direction till infinity. But in discrete filters, of course, that's never the case. So in discrete filters, whatever the overall number is, they need to sum up to 1 anyways. They cannot be like, okay, there are numbers till infinity. No, you can't say that. So whenever we construct a Gaussian filter, a discrete one, they all will sum to 1 exactly. Okay. Okay, so basic idea is very simple. Gaussian filters or Gaussian kernels are basically high frequency. Basically, they will remove high frequency components. What it means is only low pass filters or low components are only allowed to live forward or go forward. Okay, and this is the separability. Okay, so basically what we have tried to explain in these slides is, okay, so let's say you imagine this one as your Gaussian. Okay, this is a Gaussian for now. Just imagine it. You can of course normalize it. Okay, I understand you might think that this is not normalized, so we are not taking a normalized version, but ideally one should normalize the whole thing. Okay, so what we are doing here is, so you can perform a simple Gaussian and convolution. So why don't everyone so apply this Gaussian? So this is your filter and this is your function. Apply a convolution and tell me the output and tell me how it looks like. Apply this function. Okay, take this Gaussian and maybe apply, so this is 3 cross 3, but to apply it so keep padding of 1 on all sides and tell me the output. So padding is 1, and now tell me the output of each pixel. Once you apply that convolution, that is the Gaussian convolution. So give it a try, use your calculators, take like a couple of minutes and solve it properly. And just to put a noisy point, just to put a noisy point in between, let's make this 10, okay? Rather than doing this as 5, let's make it 10, okay? So let's say this is the noisy point, okay? and let's see what happens. So please everyone apply the Gaussian kernel, means apply the convolution using Gaussian kernel and tell me the output. So what's the answer? Can anyone tell me the answer here?
First line will be 40, 50, and 38.
40,
50.
38. Okay.
Second line, first one 51.
51.
Rest we are calculating.
Sorry.
No, I'm calculating.
Okay. Calculate it. No problem.
First value I got 30.
Here you got 30, 30.
Yeah.
Even I got 30.
Guys, please make sure that when you answer something, please double check your answer. This would be the normalized version, which one should use. Okay. Yeah, tell me 30, 50, 38, 51, and then if you were to do it with the normalized version,
I think sometimes we have to do padding 2.
no, padding 1, man. Why would you do padding 2 all of a sudden?
Oh, it will not give 3 cross 3.
What? Okay, so whenever you do padding 1, what it means is in all sides, extra 1 padding is added, right?
Yeah.
Cool.
Yes.
So calculate it now. This is padding 1, okay? So all of the green ones are basically zeros. So it will not give 3 by 3. That's what you're saying. Come on, guys. What is the answer?
I think it's 85 in the middle.
Okay, so this is 30. This is 50.
Yeah, these are fine.
30, 51,
85,
85. Next one,
65,
65.
then 40, 64, and last one I'm calculating.
Okay.
52.
Yeah, 52.
Okay. So I'm just taking a normalized version. Basically, you have to just make sure that you divide by 16. Okay, that's all. And then we have 40, right? That will be 2.5. 64 will be exactly 4, and okay. Now you see, basically even the original one, 10 is pretty large. Now 5, I'm not saying that it is really less, but once you see nearby around it, there are a lot of values around like 4 and 3.2 or something. Like in this circle itself, if you were to see it, it has been normalized a bit. Okay, you can say it has been averaged out, but it is not like a flat averaging, but it has been a small Gaussian averaging that it has tried to perform. Okay, so this is what it achieves, a Gaussian kernel. If you were to apply it on any signal, and if there is a noise point, it will try to bring it down a bit. Okay, now of course, depending on sigma and how big the spread is and how big your filter is, the smoothing effect have a either it might be very concentrated or it might be very large. Okay,